This is our first problem for isometric process. Please take your time to read and understand the problem. So we are given the specific gas constant and the specific heat ratio of the gas. Since heat is added, the sign for Q should be positive when we write it in our given. The mass of the gas is also given. Since volume is held constant during the process, we can say that the gas is undergoing an isometric heat addition process. Finally, the initial temperature of the gas is also given. Converting it to Rankine, we will get 550 Rankine. From this given information, we shall find the final temperature of the gas in Rankine, the change in enthalpy, change in internal energy, and non-flow work in kilojoules, and the change in entropy in kilojoules per Kelvin. Again, before we proceed to our solution, we must first sketch the PV and TS curves for this process. Since it is already stated that heat is being added to the gas, it is easier to first sketch the TS diagram. The reason for this is that the direction of the TS curve for heat addition process is simply from the lower left to the upper right. Now the direction of the curve in the PV diagram will just follow the direction in the TS diagram. Since this is an isometric process, the PV curve will just be a straight line starting from the bottom and ending at the top. We are going to make use of approximate solutions in this problem. Therefore, when we are going to compute for the final temperature, we can use our formula in getting the amount of heat transferred, in which we consider the specific heat at constant volume to remain constant. We can rearrange the equation in this way so we can isolate T2 at the left side of the equation. In this formula, Cv is the only quantity that is unknown. So by using the formula for Cv involving the specific gas constant and the specific heat ratio of the gas, we will be able to find the value of the specific heat at constant volume. By substituting all known values in our formula, we will now be able to compute the final temperature of the gas to be equal to 563.7 Rankine. The approximate change in enthalpy can be computed using this formula. In this equation, only the specific heat at constant pressure is unknown. But by multiplying the specific heat ratio and the specific heat at constant volume that we computed in the previous slide, we will be able to get the value of C sub P. Substituting all known values in our formula, we will be able to get the value of delta H to be equal to 25.2 BTU. Next, we will solve for the change in internal energy. The approximate change in internal energy can be computed using this formula. However, if you remember, this is also the formula for the heat transferred during an isometric process. So, by equating delta U to Q, we will get 20 BTU for the change in internal energy. Next, we are going to solve for the change in entropy. Based on the formulas that we presented in the previous video lecture, the change in entropy during an isometric process can be computed using this formula. Substituting all the known values in the formula, we will get 0.036 BTU per Rankine as the value of our delta S. Finally, we shall compute for the non-flow work. This is very easy to answer since we know that during isometric processes, non-flow work is just equal to 0, since there is no change in the volume of the gas. Again, we now check some of our answers if they are consistent with the direction for diagrams. The given initial temperature is 550 Rankine, while the final temperature that we computed is 563.7 Rankine. This is consistent with what we have in the TS diagram since point 1 is placed below point 2. The change in entropy is also consistent with the direction of the TS diagram. Since the value of the delta S that we computed is positive, the final entropy S2 should be at the right of the initial entropy S1. And this is what we have in our TS diagram.